Newspaper clippings of various mud volcanoes since 2000. This is a map showing the location and distribution of mud volcanoes in onshore Trinidad and offshore Trinidad. What we notice is there's a gap between the east coast and these offshore mud volcanoes where most of the BP fields are located. This is because this area is fairly rich in sand, therefore it is difficult for mud volcanoes to develop. Three items or combination of these items must be present for mud volcanism to occur. Firstly, overpressured claystone intervals. 2. Compressive forces due to tectonic activity. 3. Hydrocarbon generation and migration. With the arrival of the Orinoco Delta in Trinidad around 5.5 million years ago, between 20,000 and 40,000 feet of sediments were rapidly deposited. Much of these early sediments were clay-rich and were rapidly buried by other sands and clays. This rapid burial resulted in the water trapped in the pore spaces of the sediments being unable to escape. As these sediments are buried deeper and deeper, the pressure of the trapped water builds as overpressure. These overpressure muds behaves more like a low viscosity magma. Its active rise is facilitated by hydrofracturing and can inject structural or stratigraphic interfaces and weaken the surrounding strata. Kerr et al. 1970 analyzed mud from the Palo Seco and Moruga Bouf and compared them to lower cruise samples. The clays on the mud volcanoes are predominantly mixed layer illite, montmorillonite, and kaolinite. In the lower cruise, illite forms a larger part of the mixed layer clay. Formation samples contain 55 to 69% of less than 2 micron material, while mud volcano samples contain 33 to 44% due to mixing with silt and fine sand. Other samples from Devil's Woodyard, Piparo, and Diggity range from 19 to 66% clay, as analyzed by Yassir 1989. All clay samples, when water saturated, become thixotropic with the capacity to flow as a liquid. Thixotropic clays, when saturated with water, becomes a highly mobile fluid with great transporting power. This explains the presence of large boulders in some mudflows. Trinidad lies at the intersection of the Caribbean and South American plates. As a result, it has been exposed to multiple phases of tectonic deformation, starting from about 10.5 million years ago to the present. The compression and transpression due to plate movements created many folds that currently make up the Central Range and the Southern Range, as well as major faults. No mud volcanoes are found north of the Central Range, as faults are mainly extensional or transtensional. Mud volcanoes will develop either along networks of hydraulic fractures or fracture zones associated with thrust faults. Most of the mud volcanoes are found either near the crests of anticlines or close to major thrust faults. Most of the mud volcanoes in the onshore are found either near the crest of anticlines or close to major thrust faults. When contraction of the rocks takes place due to thrusting, localized overpressuring takes place and fluids, water, oil, and gas are injected through overlying rocks and faults, producing mud volcanoes. This is a diagram done by Pindell et al. Of 2007 to show the southern anticline with mud coming up along its core to form mud volcanoes as at Erin Bouf. This diagram is a seismic line and interpretation through the Gulf of Paria and the Pedernales area of Venezuela to show the structure of the continuation of the southern range in Venezuela. Mud volcanoes occur at the crest of the fold. Hydrocarbon generation and migration. More than 2 billion barrels of oil and 20 trillion cubic feet of gas have been produced from the onshore and offshore area of Trinidad. Generation of this oil and gas took place and continues today anywhere between 13,000 and 18,000 feet below sea level. Hydrocarbons being lighter than the surrounding source rock from which it was generated migrates upward using fractures and faults in the rock. Gas generation and migration may be one of the greatest contributors to mud volcano eruptions. It will do so by lowering the density of fluids and thixotropic clays. Also, when gas entrapped in shallow sands under the mud volcano, pressure will build until it fractures the overlying sediments and escapes as an eruption. Eruption of the South Coast in 1911 resulted in fires that could be seen from Port of Spain. Most mud volcanoes constantly emit gas, being most visible in areas that have large mud pools such as Lagon Bouf, Erin Bouf, and Lo Michel. DeVille et al. In 2009 estimated discharges. The following items or combination of these items are expelled from mud volcanoes: water of variable salinity, mud, which includes clay and fine particles, and classed of different lithologies, oil, and gas. Mud erupted from mud volcanoes and the vents and pools tend to be atmospheric or just below atmospheric temperatures. This is the result of rising gas in the mud expanding and cooling the mud. DeVille and Gurley in 2009 confirmed this process at Palo Erin Bouf, and Lagon Bouf. Analyses of gases released from the mud volcano indicate that it is predominantly methane. These gases burn with a yellow to orange smokeless flame and are generally odorless. Battiani et al. In 2010 analyzed carbon-13 values which indicate the gas is thermogenic in origin and the high methane content is due to separation during migration. Analysis of noble gas radiogenic isotopes has shown the resident time is shorter for the gas expelled by mud volcanoes than for gas present in producing fields. Thus, gas expelled is not from fields but from deep kitchens. Water analysis by Dia et al. In 1999 revealed that the unique methane content, large positive O18 shifts, as well as boron, lithium, and barium contents revealed that the fluids originated at depths greater than 3 kilometers. These fluids, originally seawater, as they rise, mix with the less deep reservoirs and meteoric waters. This suggests a recharge mechanism that contributes to mud expulsion. Castrec-Ruel et al. In 2002 indicate the maximum age of water circulating in the mud volcano system is plus or minus 9 million years. Two types of mud volcano activity are seen in the onshore of Trinidad: quiescence, which involves continuous venting of gas and mud, or catastrophic, episodic large eruptions. Quiescence involves continuous venting of gas and mud associated with areas with no historical reports of eruptions. Typically, the areas consist of a large mud and water-filled pool or small point sources, as in Quinam, Erin Bouf, Lagon Bouf, Palo Seco, Marac, Lo Michel, and Digity. Catastrophic. Episodic large eruptions, the areas are quiet for periods ranging from 15 to 50 years before a violent eruption, expelling large volumes of clay, water, and rock, as in the recent Tabaquite and Devil's Zodiac eruptions, also Piparo, Chatham, and Anglais Point. The following series of diagrams indicate how gas, water, and mud vertically migrate from deep footwall traps, along faults, migrate into shallow reservoirs, pressurize them, and eventually the overburden fails and there's an eruption. Earthquakes. A number of researchers around the world have invoked earthquakes for the trigger for mud volcano eruptions. While the data suggests this may be true for Azerbaijan, there has been no such relationship found in Trinidad. DeVille and Gurley in 2009 compared seismic activity with mud volcano eruptions during 1900 and 2008 and could not find any correlation. The 6.9 magnitude earthquake with an epicenter in Venezuela that hit on the 21st of August 2018 was the largest to have hit Trinidad in more than 100 years. Its only geological consequence was the reactivation of a large landslide in the Locero area in proximity to the Erin Boof. However, there was no change in the level and location of mud vent activity. Using data collated by Deville and Gerley from 2009 of 6 historical mud volcano eruptions and updated with the Tabikit mud volcano eruption, at the time of eruptions for the mud volcanoes was examined. The average varies from 14.7 to 50.5 years. Devil's Woodyard appears to be the most regular, with an average of 27.7 years between eruptions. If one pushes the event correlation envelope, a pattern of eruptions appears to emerge, where 4 or 5 mud volcanoes erupt within a few years of each other. Will this trend continue with the recent eruptions? Schiller in 1967 classified mud volcanoes by the type of cone and size of vent. Type A, the cone has sides greater than 20 degrees and a vent of a few dozen cm. Type B, the cone has sides 5 to 20 and a vent of a few dozen cm. Type C, cone has size less than 5 degrees and a vent between 1 and 2 meters. Type D, shaped like a caldera and a vent of several meters across. And type O, a small mud hole with a vent of a few cm. Type A mud volcanoes, example Cascado, Palo Seco, and Diggity. In type B mud volcanoes, the cone has sides of 5 to 20 degrees and a vent of a few dozen centimeters, as at Erin and Lomichel. In type C mud volcanoes, the cone has sides less than 5 degrees and vent between 1 to 2 meters, as at Erin, Peparo in 2012, and Palo Seco. The type D mud volcano is shaped like a caldera and has a vent of several meters across, as at Le Inverse in Cedrus, Erin Boof, Lagon Boof, and Lomichel. The type O mud volcano is a small mud hole with a vent of a few cm. Examples are found at Erin Boof, Cascado, Devil's Woodyard, Peparo, and Marac. A feature of all active mud volcanoes is an area with no or very little vegetation, especially in forested areas. This clearing is called a tussock after Helm of 1940. Examples are seen at Peparo, Devil's Woodyard, Diggity, and Erin Boof. There's a list of references